Hoffmann Technics is the major Swiss manufacturer of electric machines and has been uniting scientific engineering and high-tech industrial potential along with innovative solutions in the field of electric drives for more than 60 years. The main manufacturing site of the concern is the Leningrad Electric Machines Engineering Plant, LEZ. The enterprise has many years' experience in the development and manufacture of large electric motors, turbo and hydro generators, and variable frequency drives. The products from the St. Petersburg plant are used in nuclear power engineering, in the hydropower industry, in heat and power engineering, as well as steel plants, and in all mining and processing enterprises in the petrochemical and cement industries. Nowadays, the St. Petersburg plant has a complete production cycle, including the development, manufacture and delivery of electric motors of more than 500 dimension types, with overall dimensions of up to 10 meters in diameter and weight up to 165 tons. These are squirrel cage and slip ring wound rotor induction electric motors which are used in industry for the manufacture of pumps, fans, crushers and other devices with high rotational speed. Our plant also manufactures synchronous motors, turbo and hydro generators. Their fields of application are in the heated power engineering and hydropower industries. These motors are also used to drive compressors in mills at ferrous and non-ferrous metallurgy enterprises and at cement plants as well. The production process is identical for different types of electric motors. Still, there is a considerable difference. The motor consists of two basic components, a standing stator and movable rotor which rotates inside the stator. There are numerous windings in the stator. The winding's electric current sets up a concentrated magnetic field which rotates the rotor. One of the first operations is to sheet materials nesting layout by means of gas cutting. This operation is carried out with NC machine tools guided by a controlling program. The sheets are then welded into an integrated body. Then, welded seams are pneumatically dressed after the assembly of the main stator body. The frame mounting faces are machined by a rotary table milling machine for stator iron stacking. The milling machine is equipped with NC rack to provide the required accuracy of internal surface machining. The magnetic core is made along the stator body circumference after completion of the stator body manufacture. This core is another hollow cylinder made of a stack of 0.5 mm thick electric steel laminations. The magnetic core is assembled from separate segments since the stator diameter sometimes amounts to several meters. Packing washers are installed between certain numbers of the segments. Various methods are used to manufacture the segments. One of these methods is stamping. The stamping machine blocks stamps to a maximum capacity of 800 tons, stamp segments or round hole sheets in the case of a small dimensions motor assembly out of steel rolls. There are slots on the outside of the segments which are later used for copper winding installation. Hydroabrasive cutting and laser cutting NC machines are used at the plant as alternatives to the stamping machines. Such machines are mainly used for small volumes of production because being slower than the stamping machines, they don't require time-consuming readjustment prior to the start of the manufacturing of a new batch of segments. The thin segment has somewhat bent edges after stamping. This defect is eliminated by means of scraping with a special machine tool where the part is machined with emery cloth. Totally smooth surface of the segments is coated with special varnish to reduce power losses caused by magnetic circuit eddy currents. Then the segments are placed into a varning machine where they go through three main stages: coating with varnish, drying and cooling. The magnetic circuit may then be assembled and pressed together. Copper winding is installed into the slots after the completed manufacture of the magnetic circuit. These are either bar or coil windings depending on the motor type. manufacture of the coil includes several stages. Firstly, insulated wire is boat-shaped wound for electric motors below 6 kilovolts. Then the wire is additionally insulated if turn-to-turn insulation is required for high-voltage machines of up to 11 kilovolts or 13.8 kilovolts in 60 Hz. After that, the winding is made in the form of a circle with subsequent boat-shaped stretching. The coil is shaped from the boat of a stretching machine. Coil shape and the overall dimensions are checked in a model imitating the stator core. The winding manufacture is the most important stage of the motor manufacturing process. The motor's long service life and power retention depends directly on the winding quality. Part of the stator coils and winding sections, up to approximately the middle, is insulated manually. The rest of the winding section and the slot section are insulated mechanically. Our enterprise also has a set of bar bending and insulation taping equipment, which is used for the manufacture of large hydro generators. The set consists of two machines. One is used for the bending of end winding sections, the other for the insulation taping all along the bar. The insulation tape is wound with a certain tensioning effort, which is adjusted automatically to the required value. St. Petersburg plant has many years of valuable experience in VPI, or the Monolith 2 system insulation of bar and coil windings with dry tapes, as well as in resin-rich insulating with impregnated tapes. The essence of the first method, called Monolith, is as follows. A stator with dry tape insulated coils, which have been installed into it, is put into the autoclave. The autoclave is evacuated so as to remove volatile substances and to provide for the high-quality insulation impregnation. Then a compound is fed from a mixing tank and held under pressure. After that, the stator is removed from the vessel and put into an oven to dry. The essence of the second method is as follows. Either bars or coils insulated with impregnated tapes are put into an empty bath. The bath is placed into a mica-filled unit and the bars or coils are vacuumized. Heated bitumen is then fed from a mixing tank into the mica-filled unit. Thus, the insulation is pressed and baked. The mica-filled unit is highly productive equipment and allows the production of hundreds of coils and dozens of bars in a shift, providing for the pressing of not only slot section insulation, but also of end winding insulation, thus making it possible to carry out high voltage tests for both sections of the coil. Such technologies result in coils of the highest quality. The finished winding is installed in longitudinal slots during induction motor stator assembly. Insulating pads are placed at the slot's base between the top and bottom layer coils, as well as under slot wedges used during the winding installation. The coil and winding sections are tied to retaining rings as the winding is installed. To create the rotor, a rotary component of the machine, a shaft is turned on a lathe to the required configuration. The rotor shaft is machined with the shaft bearing journals control. The magnetic wheel, intended for the installation of poles, is manufactured during the synchronous motor manufacture stage. The wheel holes required for the installation of the poles are drilled in compliance with the preliminary given program. The final stage of the motor assembly is the rotor installation into the stator. In the case of large electric motors which are used at hydraulic power plants, this operation may require several hours. This is to be carried out with the utmost care to avoid damaging the stator winding. Numerous tests are conducted at the enterprise in compliance with the IEC norms requirements. High voltage tests are carried out prior to finishing the bar's installation into the stator. An electrode is attached to the bars. This is then connected to the grounding strip. Then the test circuit is connected and the test voltages of 25 kilovolts and 50 kilovolts are applied to the end winding section and to the slot section correspondingly, both for 1 minute. The test samples have passed the test satisfactorily if there is no insulation breakdown. The voltage endurance test is performed to determine the insulation service life. Two factors influence the insulation: a temperature of approximately 100 degrees centigrade and increased voltage. The successful outcome of the voltage endurance test guarantees the insulation service life for 25 years. The thermal and mechanical stability of the insulation is determined during thermocycling tests. To measure the insulation resistance, 2.5 kV of DC voltage is applied. The measured insulation resistance value shall not be less than 500 milliohms. The stator winding connection circuit is subject to thermo-visual control. The motor is then subject to various tests on a test rig after assembly has finished. Noise level, vibration severity and air gap efficiency, power factor and slip ratio, initial starting torque, as well as other parameters are measured during the tests. Safety of the motor operations is also confirmed during these tests. Induction and asynchronous motors manufactured by the St. Petersburg plant have been operating in various industries for many years. They have been serving people reliably, making their life more comfortable and their work easier and safer. Hoffman Technics is your expert in electric motors and drives.